Hello. This is an example problem for how to use the method of sections when you have more than 3 members for where you cut the truss. You can see we have a problem here. It says determine the force in members DC, HI, and JI. So let's locate those. I'm just going to put a red line through them. We have DC, we have HI, and we have JI. So those are the 3 members that it wants you to solve for. And typically what we do in the method of sections is we make a cut. We get out our hacksaw and we cut through the truss. And then we use rigid body equilibrium. Now with rigid body equilibrium, as we know, you only have 3 total equations. You can either use sum of the force in X, sum of the force in Y at 1 moment, 2 moments, 1 force, or all 3 moments. But you always only have 3 equations to solve for. So that means you can solve for 3 unknowns. If you notice in this problem, if we cut through all of those 3 members and we go right through, we're going to cut through 4 members, which means we'd have 4 unknowns. And obviously we can't solve 4 unknowns with 3 equations. So let's go ahead and give that a try first. It actually gives you a hint on this when it says suggest use the section shown. And the section shown, you can see the 2 blue lines. We're going to pretend like we didn't get that hint and see what happens if we just cut straight through it. We're also given a few things, so let's write our givens down. We are given that P1 is 1,210 pounds and P2 is 1,570. And we're supposed to find FDC, FHI, FJI. Oops. Okay, let's go ahead and get started. The first choice, we know we're going to cut through it, and I'm going to just go ahead and cut through all of those members we're looking for. I'm going to do a straight cut to get started with. So if I do a straight cut, I get to choose either the top or the bottom. Think to yourself, which of those two would you choose? When I look at this, I definitely choose the top one. And the reason for that is simple. There are no supports in the top one. There's only 2 forces acting on it, P1 and P2, and those are given. So that means we don't have to do step 1. What I often call step 1 is drawing a free body diagram of the entire system and solving for the supports at A and B. We don't have to do that because it's not going to be part of the free body diagram that we're going to draw. In many other problems, you're going to cut through it and you're either going to choose the right or left hand side. And in a lot of those problems, you'll need to do step 1 because you need to solve for those supports. So I'm going to go ahead and draw a free body diagram of the top of this truss. I'm going to draw it nice and big so that I have enough room to put my forces. Okay, that's the part that we're going to cut above the red line. I'm going to put my forces on now. I'm going to have my P1, which is 1,210 pounds. I'm going to put my P2, which is 1,570 pounds. And now I'm going to put all of the members we cut through. And I'm going to draw them all in tension because I find that easier to keep track of my signs. I'm going to call that F, H, I. And we cut through JI, F, JI, we cut through JC, F, JC, and we cut through DC, F, DC. Okay, let's see where we can go from here. So now what I want to look for is I want to look for opportunities of only having 1 unknown. If we look at that, there's not going to be very many areas where we would just have, there's actually going to be no options for just 1 unknown because we have 4 of these. So we can choose maybe the sum of the moments about point J, and that's going to knock out 2 of them. So if we do sum of the moments about point J, the JI and JC vectors, therefore don't make a force about that about that point because they pass right through it. So we're just going to add the rest of them. We're going to have a positive 1210 pounds times the distance from there to J. The perpendicular distance from there would be the 6 plus the 9, so we're going to say 15 feet. Okay, then we're going to have another positive FHI, and FHI is just going to be, sorry, I forgot my plus, FHI. We're going to multiply that by its distance from J, which is 6 feet. Okay, then we're going to have FDC, which is negative, because I'm putting my thumb pointing up at J, I'm pointing my fingers towards the force, so I tend to curl my fingers backwards, which means they are negative. That's with the right hand rule. And then negative 1570 pounds times 15 feet equals 0. Okay, that's my first equation. Do a little bit of algebra there so I can get my FHI in terms of FDC. Great. Okay, I'm going to leave it there for now, and then I'll get out my calculator in a minute. We'll get some more information about that. Okay, so that was some of the moments about point J. Now we can get some more information if we want to do some of the moments about either, well, we can do some of the forces in the x direction is going to give us a relationship between FJC and FJI. So some of the forces in the x direction is equal to 0. And you can see that we have to figure out an angle here. We have the angle in the drawing up there, this green angle here. That would be 6 feet going down this way, and also 6 feet over here. So we could take the inverse tangent of 6 over 6, which is the inverse tangent of 1, and we find that that's 45 degrees. So that means that this angle right here is 45 degrees. If that's 45 degrees, then the x components are going to be the cosine of 45 on both of those. So we're going to have that FJC times the cosine of 45 degrees minus FJI times the cosine of 45 degrees equals 0. Do algebra on that, and we see that FJC equals FJI. Okay, so that's a pretty simple equation for us. Okay, so now we're going to do some of the moments. We could choose to do either some of the moments at D or some of the moments at H. So I'm going to go ahead and choose H. Some of the moments at point H equals 0. From point H, we were going 9 feet over to the 1210, and it would be positive, so we'd have 1210 times 9 feet. And then we're going to have the y component of Ji is going to make a moment, and the y component of Jc is. And those will both be negative, so we're going to have negative FJI. Now it's the sine for the for the y component of it. We use the x component above as a cosine. Sine of 45, and that's going to be multiplied by 6. And we do the same thing with FJC, because that y component is acting at the same location, and it's also the sine of 45 degrees. times 6 feet. Great, there's just 2 more. We're going to have negative FDC, and the distance from that is going to be 6 plus 6. We got 12 feet, and then negative 1570 pounds times the total distance. That would be 12 plus 9, so 21 feet. Equals 0. In this one, it looks like we have 3 unknowns, but we can use this information up here to make it only 2 unknowns. And you can see that we have FJC and FJI are the same thing, so let's just make them both FJI. And we can get JI in terms of FDC. Okay, there we go. We now have 3 equations, and you notice that we can't really go any further algebraically, and this is where we run into an issue. So we now have that we have FHI in terms of FDC, we have FDC in terms of FJI, and then we have FJC in terms of FJI. So there's no equations that we can really go any further on. I could plug my FDC, I could plug this equation up into here, but that wouldn't really solve anything for us. All that would give us is it would give us FHI in terms of FJI. That doesn't move us along. And we expected this, and we should expect this, because we had 4 unknowns and only 3 equations. We now have those 3 equations, 1, 2, and 3. And so that's all we can do with this free body diagram. Now what we're going to do is get some more information. How do we get more information? We make a different cut, which means we make a different free body diagram. So I'm going to go ahead and draw that second free body diagram, and let's get a little bit more room here. Okay, so all I've done here is I've kept the 3 equations we solved so far, and I cleared out a little room for myself so I can draw another free body diagram. So what I'm going to do now is I'm going to make another cut, and it doesn't really matter where that cut is. We have to make sure that we get at least 2 of the variables that we're interested in. So I'm going to follow the suggestion of the book and use this second cut up here. If we use that second cut, I can make a new free body diagram. My new free body diagram looks like this. Okay, there's my new free body diagram, and now I have to put in all the forces acting. And I have to put the forces of the members that I cut through. So I have my FDC, and I have my FDJ, I have my FHI, I have my FHJ. Okay, so now we have a free body diagram, and if we look at the 3 equations that we have already, we don't actually need to have all of we don't need to answer this entire free body diagram because we have 3 equations and 4 unknowns, so we really only need one more equation. One thing that you notice here is if I knew what FDC was, I could plug FDC in here and I would get my FHI. I could also plug FDC in here and I'd get my FJI. Then I would have all of the 3 things that were asked for. So if I have FDC, I can find the other 2. Looking at this free body diagram, do you see any way we could get FDC? Hopefully you see right away that we could take the sum of the moments about point H. We take the sum of moments about point H, there's only one unknown left that will cause a moment. So let's do that. Sum of the moments about point H is equal to 0. Point H, you have FHI, FHJ, and FDJ all pass right through that point. So they're going to have 0 distance between the line of action of those forces in the moment. That's why this free body diagram is really handy. So we can just say that it's going to be 1210 pounds times 9 feet for that force. And then we would have from the FDC, we'd have negative FDC times the distance between H and DC, which is 12. Then we'd have negative 1570 times the distance there, which is 12 plus 9, or 21 feet, equals 0. Nice, we only have one unknown, so we can find FDC. FDC is going to be equal to 1210 times 9 minus 1570 times 21 all over 12. Top is foot-pounds, and the bottom is feet. So we'll end up with pounds, which is what we're hoping for. I'll plug this in the calculator real quick. Okay, so I'm going to take a second to make sure this makes sense. If I look at my FDC, it's saying it's in compression. I drew it in tension because I like to just keep things in tension, then if they're negative, I know they're in compression. And if I look at this, we have P1 and P2 are both pushing down, so that would tend to compress this whole thing, push the whole, all of the members down, and FDC is pointing up. So it makes sense to me that would be compression. So that's one of my answers. Now I can find FHI directly by plugging this in right here. So my FHI equals 1570 times 15 minus 1210 times 15. I'm going to plug in plus my negative 1840. It's very important you keep that negative in there. Times 6 all over 6. And again, our units are foot-pounds on top. I shouldn't put the units in there. Foot-pounds on top and feet on the bottom, so we're going to end up with pounds when those 2 feet cancel out. And we can do this calculation to find our FHI. We get negative 940 pounds. For the same reason, it makes sense that that one would be in compression. It also makes sense it would be less compression because P1 is smaller than P2. So we look like we're doing pretty good. Now I have to figure out my FJI. So I'm going to go up to equation number 2 on the top, and I'm going to resolve that equation for FJI. So FJI 2 times FJI sine of 45 times 6. I brought that over to the left-hand side, so now it's positive. Will be equal to negative 12 times FDC plus 1210 times 9 minus 1570 times 21. Okay, now I can take that and divide by the 2 sine 45 times 6, or that's 12 sine 45. So FJI is going to be equal to negative 12 FDC plus 1210 times 9 minus 1570 times 21, all over the top of 12 sine 45. Go ahead and solve that one. We plug in our FDC, which is negative 1840, and we get 0. FJI equals 0. Now that one at first might be a little puzzling, but if we look at it and we say, okay, well, are there any X forces acting on this system? Since there are no X forces acting on this system, we can see that unless A and B were mounted with an internal tension, which we know it can't be because B is a roller, there'd really be no reason for AK and KB to have any force in them. If AK and KB have no force in them, that means that AI and AC are holding all the weight straight up and down, which gives no reason to have IJ or JC have any force in them. So it makes sense that we would have 0 here. So our 3 answers are known. We've got, and we're going to report them in tension or compression. So we're going to write those out as FDC equals 1840 pounds, and it's in compression. FHI equals 940 pounds, and it's in compression because it's negative. And then FJI equals 0 pounds, neither compression or tension. Those are our 3 answers. Hopefully this was helpful. Please let me know if you have any questions.